Imagine a shield so strong it can stop bullets mid-air, absorb impact without a scratch, and spin like a perfect boomerang. Yeah, we're talking Captain America's Vibranium shield. But here's the question. Could this shield actually exist in our world? And if it did, would Captain America survive using it? Let's break down the science and maybe ruin your childhood just a little. Vibranium in the Marvel Universe is basically magic. But let's translate it into real science. According to the comics and movies, vibranium has some incredible properties. First, it absorbs nearly all kinetic energy, meaning it can stop a punch from the Hulk without even budging. Second, it's super durable, almost indestructible. Third, it's ultra lightweight for its strength. And finally, it can bounce off surfaces with perfect elasticity, like a super-powered billiard ball. So, how does this stack up against real-world materials? Let's start with titanium. It's incredibly strong and relatively light, which is why it's used in aerospace and high-performance gear, but it doesn't absorb energy like vibranium. If you hit a titanium shield with a hammer, that energy is going right into your arm. Ouch. Then we have carbon nanotubes. These are mind-bogglingly strong on a microscopic scale, stronger than steel, but they're brittle. Imagine a bundle of uncooked spaghetti, strong in one direction, but snap it, and it's done. A shield made of them might shatter under the right kind of impact. And what about graphene? This is the wonder material of the 21st century. It's a single layer of carbon atoms, making it extremely strong, flexible, and lightweight. But we can only produce it in very small, very expensive sheets. Building a full-size shield out of it is currently pure science fiction. So if you tried to build a vibranium shield in your garage with steel and duct tape, it would probably dent badly. Let's do some quick math to really understand the forces at play. A standard 9mm bullet carries about 450 joules of energy. When Captain America blocks a hail of gunfire, he feels no recoil. The shield just soaks it all up. From a physics standpoint, that means the shield is absorbing hundreds, maybe thousands of joules of energy every second. What happens to real metals? They deform, they crack. Or, more painfully, they transfer that energy directly to the person holding them. Newton's laws are pretty stubborn. For every action, there's an equal and opposite reaction. If a bullet hits a shield, that force has to go somewhere. With vibranium, it just magically vanishes. In real life, that force would send the shield and your arm flying backward. Try this at home. Or actually, please don't, unless you really enjoy the thought of dislocated shoulders. Now for the really fun part, the boomerang physics. Cap throws his shield with impossible precision. It spins perfectly, ricochets off walls, takes out a few bad guys, and then gracefully returns to his hand. Could we ever do that with a real shield? To make this happen, you need a few things to go perfectly. First, rotational inertia. The shield has to maintain its angular momentum to keep spinning stably through the air. This depends on its mass and how that mass is distributed. For it to be a stable aerofoil, it needs to be perfectly balanced. Any imperfection would cause it to wobble and crash. Then there's air resistance. To fly smoothly and predictably, the shield would need a shape that minimizes drag, something real-world shields aren't designed for. A typical shield is built for defense, not aerodynamics. Let's look at the numbers from a simulation. The vibranium shield weighs about 12 kilograms or 26 pounds. To throw it with the kind of spin we see in the movies, Captain America would need to generate an insane amount of torque, something like 50 Newton meters. An elite athlete might be able to do that, but the precision is the real killer. With a real-world metal shield of that weight, it would either spin off wildly into the crowd or just drop to the ground like a very expensive, very disappointing rock. Even the most skilled discus thrower couldn't replicate Cap's ricochet shots. The angles, the spin, the surfaces, everything would have to be calculated with superhuman, computer-like accuracy. You'd basically need to be a Marvel mutant to pull it off. So, if we were serious about building a real-world vibranium substitute, what would it take? What's the closest we could get? First, we'd need an energy-absorbing alloy. Our best bet would be a composite material. Imagine a matrix combining the strength of carbon nanotubes, the flexibility of graphene, and the durability of a titanium alloy. This material still wouldn't absorb 100% of kinetic energy like vibranium does, but it could potentially dissipate a significant amount, turning a bullet's impact into heat. With some serious padding on the inside, it could maybe deflect small arms fire without breaking your arm. Second, the weight. The shield has to be light enough to be thrown effectively, ideally under 15 kilograms. The problem is, our strongest real-world alloys are dense and heavy. Making something both incredibly strong and incredibly light is the holy grail of material science. The more strength you add, the more weight you usually get, making it harder to handle and spin. Third, perfect elasticity. For the shield to bounce off surfaces without deforming or losing energy, it needs to be perfectly elastic. This would require an exotic molecular arrangement that we simply don't know how to create. Any real material will lose some energy on impact as heat or sound, and it will eventually deform. So your garage project is still just a fancy frisbee. And Captain America would probably cry if he saw it. Now for the big climax. Let's just say we did it. Against all odds, our scientists create a vibranium-like shield. It's ultra-light, ultra-strong, and has some energy-absorbing properties. Could a real human actually use it like Captain America? Let's talk about throwing it. The human arm can generate a decent amount of force, but a throw topping out at 70 meters per second is probably the absolute limit for an object of that shape and weight. You could definitely hurl it, but not with the speed and power Cap does. And the ricochets? That's where it all falls apart. To get those perfect bounces, you'd need zero air drag, perfectly flat and hard surfaces, and an initial throw calculated down to the nanometer. In a real-world combat scenario with uneven surfaces and chaotic conditions? Not a chance. The shield would hit a wall and just clatter to the ground. So what's the realistic scenario? A shield made from our hypothetical supermaterial could probably block bullets, especially if it's light enough to hold steady. You might survive a firefight you otherwise wouldn't, but throwing it for a boomerang effect? Probably not. Spinning it with enough force to knock out enemies? Only if your biceps are the size of a small car. So in the end, if a real human used a real-world version of a vibranium shield, you might survive a bullet. But don't expect to become a world-class superhero overnight. Captain America's shield is more than just a weapon, it's a physics nightmare, a material science fantasy, and a true cultural icon. And while we can get closer and closer in our labs with new discoveries, the truth is, reality will probably never match the magic of Marvel. At least, not yet. If you loved watching science poke holes in your favorite superhero dreams, do us a favor and smash that subscribe button like Cap smashes bad guys. Join us here at SciNex, where physics fights fantasy and curiosity always wins. Thanks for watching.